In the previous lectures, using differential analysis, we derived the continuity equation given by this equation. So the vector form of that equation was divergence over V equal to 0, and we also derived the vector form of the Navier-Stokes equation for incompressible and Newtonian fluid. Okay, so we derived this equation, which states that the total force on my fluid element is equal to the pressure force per unit volume plus the viscous force per unit volume plus the body force per unit volume. Okay, the applicability of these equations will become more clear when we'll solve some problems using these equations. Okay, but before that, let's first understand the boundary conditions that are commonly encountered in fluid flow analysis. So the first most used boundary condition is, so let me just first write the title. So we are now studying the boundary conditions encountered in fluid flow analysis. So the first boundary condition is no slip condition. It states that for a fluid which is in contact with a solid wall, the velocity of the fluid must equal to that of the wall. In other words, we can say that the relative velocity between the fluid and the wall is 0. Okay, so the relative velocity between the fluid which is in contact with the wall and the wall is 0. So let's say that you have a solid boundary. So let's say this is your solid wall. Okay, and let's say the fluid is flowing like this. Okay, so let's say the fluid is flowing like this, and let's say your solid wall is stationary, or let's say moving with some velocity u. So let's say in one case the wall is stationary, and in other case this is moving with velocity, let's say u. Okay, so what can you say about the fluid which is in contact with the wall? So let's say there is a fluid layer which is in contact with the wall. So I am just marking it with this blue color. So what can you say about this fluid layer? So the velocity of this fluid layer is 0 because the velocity of the solid wall is 0. Okay, and in this case the velocity of the fluid layer which is in contact with the solid is u. Okay, so this is what no slip boundary condition tells me. Since I am discussing about the no slip condition, let me also briefly discuss about the slip length. Okay, let's again consider your solid wall. Let's say this is your solid wall. Now there have been some studies where people have found that if for very small channels, if this distance is of the order of nanometers, then they have found that no slip condition does not hold within a few nanometers of the wall. So in that case, let's say if the velocity profile is like this, Let me just draw the velocity profile first. Let's say this is your y-axis and let's say the velocity profile. Okay, so in that case there is the no slip does not hold, so it should not start from 0. So let's say this is your y, and let me just draw it like this. Let's say the velocity profile is like this, and let's say this is your UF. Okay, and let me just extrapolate this y-axis down to solid. Okay, so in that case what they do is, since this UF is not 0, what they do is they plot or they construct a tangent at this point, and this length at which this tangent intersects the axis, this length is called the slip length. Okay, your B is then called as the slip length. So in case of when no slip, so if no slip holds true, then in that case B is equal to 0. Okay, and B is not equal to 0 when no slip condition does not hold true. Okay, so this should be nanometers like this. So I just extrapolated the length scales, exaggerated the length scales. Okay, so we can define slip length as extrapolated distance from solid surface at which the tangential component of velocity, or let's say at which the relative at which the relative tangential component of the velocity of fluid becomes 0. Okay, the next boundary condition that we have is the interface boundary condition at the interface of two immiscible fluids. So consider a fluid B and consider a fluid A. They both fluids are immiscible to each other, and let's say there is an interface dividing the two fluids. Okay, so what does this interface boundary condition tells me? It tells me that the velocity at the interface of the fluids will be equal, and second, the shear stress at the interface will also be equal. Okay, so what it means that, so let's say if I have a fluid parcel corresponding to fluid B here, and let's say if I have a fluid parcel corresponding to fluid A here, then the velocity of that fluid parcel in B and the velocity of that fluid parcel in A, which are just adjacent to the interface, that velocity vectors will be equal. So in this case, VA vector is equal to VB vector, and the shear stress at the interface will also be equal. So in this case, tau s at A, or tau s on the fluid parcel corresponding to fluid A will be equal to tau s corresponding to the fluid parcel B. Okay, So these were the boundary conditions that are commonly encountered in fluid flow analysis, and we'll be using this particularly we'll be using no slip boundary condition to solve some problems. So let's use the equations that we derived and these boundary conditions to solve some problems. So let's take our first problem. So the problem reads as follows: a fluid is flowing between two parallel plates with length L and width W. So there are two parallel plates. The side view would look something like this. So this length is L, and there is a fluid which is flowing inside these plates. This length is L. It is given that the separation between the plates is H, and the width which will be into the plane, that width is given by W, and it is written as H is very less than L and W. Okay, now if the top plate is moving with constant velocity u along x-axis, the question was actually it is moving with constant velocity u along x-axis, then find first the velocity profile of the fluid and then the direction of the shear stress on the top and the bottom plate. Okay, so we have to find the velocity profile, something like this, okay, of the fluid, and the direction of the shear stress on the top plate, on this plate, and on the bottom plate. Okay, so since nothing is given about the bottom plate, we'll assume it to be stationary. Okay, all right, so let's start solving the problem. So first, now to simplify the problem, let's make some assumptions. So the first assumption that we'll make is the steady state flow. In this case, the fluid is flowing because of the driving force, because of the motion of the plate, motion of the upper plate. Okay, and this plate is moving with a constant velocity which is independent of time. Okay, well, it's a reasonable assumption that we can also assume that the velocity which will be developed inside this fluid will also be independent of time. Okay, that is del V by del T is equal to 0. Okay, all right. Now if the top plate was moving with a time dependent velocity, then we cannot make this assumption that del V by del T equal to 0. Okay, so this should be clear that for this case this is a reasonable assumption. Okay, the second assumption that we can make is that since it is given that this H is very less than L and W, we can assume that flow is nearly independent in x and z direction. Okay, or we can write the velocity vector which was given as ui hat plus vj hat plus wk hat, and since we are assuming that there is no flow along x and z and also the variations are not along x and z, then we can assume that this so this tells me that v vector will be just a function of y. Okay, so it is independent along the directions x and z. I cannot say currently about the magnitudes, but if I am saying that the flow is independent of x and z, then this v vector will be just a function of y, and it will not be a function of t because we have just said that it is a steady state flow, so that's why will just be a function of y. Okay, the third assumption that we'll make is since the plate is moving only along x-axis and the gap h is very very small, we can fairly assume that the velocity of the fluid along y and the velocity of the fluid along z will be 0. So we can assume that v and w are nearly 0 and v vector will be nothing but now u, which will be a function of y I hat. Okay, now with these assumptions let's try to solve the problem. So now, since it is given that the fluid is, well, it's not explicitly written about the fluid, so we can assume that the force assumption is that we can assume that the fluid is incompressible. Okay, and nothing is said about the whether the fluid is Newtonian or not, so we can also assume that the fluid is Newtonian, that is its viscosity will remain constant, and thus we can use the two equations, the continuity equation which tells del v divergence over v equal to 0, and the second equation which was our Navier-Stokes equation, which was rho dv by dt equal to minus grad p plus mu grad square v plus fb. Okay, so now since the symmetry of this problem tells me that I should take only the Cartesian coordinates, let's write these equations in x, y and z coordinates and then solve the problem. Yeah, before that let's just take this continuity equation divergence v equal to 0, and we just argued that v vector will be u, which is a function of y I hat. Okay, so in that case, if we take divergence in Cartesian coordinates, this divergence vector is given as I hat del by del x plus j hat del by del y plus k hat del by del z. So just operate on this and put this equal to 0. What you will get? You will get I hat, or I hat dot I hat will become 1, and rest of the terms will give me 0. So this will give me del u by del x, u which is a function of y equal to 0. Okay, but this we already knew. Since we knew that u is only a function of y, then obviously del by del x of u of y will be 0. So this equation does not give us anything new. Okay, now let's write this Navier-Stokes equation in the 3 coordinate axes and try to figure out the velocity profile of the fluid. Okay, so let's just write it. So these are my x, y and z momentum equations, okay, in the Cartesian coordinates. Okay, now since we know that v, and so if your v vector is given as u I hat plus v j hat plus w k hat, then I know that this v and this w are 0. Okay, and we can see that in this equation and this equation mostly v and w are there. So then let's first solve the y momentum and the z momentum equations. Okay, alright, so let me just first write. So y momentum equation, now you can see that v0, and also it's a steady state flow, so this term will be 0. So let me just mark it with some other color, or let me just mark it with blue. So this term will be 0. Then we have del v by del x, so v0, so wherever you can see v, just put it 0. This is 0, then you have this is 0, this is 0 and this is 0. Okay, now please note that the problem that we are studying is the side view of that problem is this. So these are my 2 plates, okay, and this is my fluid is there inside the inside between these plates, and this plate is moving at velocity u, and just be careful with the axis, because in this case what I've done is my y is in the vertical direction, so that's why gy will be non-zero and gz and gx will be 0. Okay, alright, so let me just rub this. This is not be useful to us while writing the y momentum equation. So now I just said that gx is equal to 0, so let's just put this equal to 0 and this put equal, let's put this equal to 0. So what we are left with is rho gy is equal to del py using this y momentum equation. So we have rho gy is equal to del p by del y, and what is gy? Gy is nothing but g only. Okay, so we get this equation after solving the y momentum equation. Okay, now similarly let's solve the z momentum equation also. So solving z momentum equation, let's see the z momentum equation. Now since we argued that w is 0, so let's just remove all the w terms. So these all terms will be 0, and we're left with del p by del z equal to 0. So del p by del z equal to 0. So what does this tell you? This tells me that p is a function of x and y. Okay, it's not a function of z. Alright, but in our problem the flow is driven because of the upper plate, so there is no pressure difference that is driving the flow. So with that argument I can say that my pressure P is not a function of x. Okay, since there is no pressure gradient which is driving the flow. Okay, so in that case, if I have P not a function of x, P just a function of y, and P not a function of z, then can I write, so let's just mark this equation as 1, this equation as, this part as 2. Now but 1 told me that rho g is equal to del p by del y. Okay, and 2 tells me that P is only a function of y. So can I write this partial derivative as complete derivative? So this becomes rho g is equal to dp by dy. Okay, and this P will become rho g y plus some constant. Okay, now since del p by del x is 0, where do we have del p by del x? This is our del p by del x, so this is 0. Now focus on the x momentum equation. So let's now focus on the x momentum equation. So wherever v and w are there, just put them 0 since they are 0. So this will be 0, this will be 0, since it's a steady state flow, this will be 0. Then okay, rest of the terms are not 0. No, del square u by del x square will be 0. Why? Because we argued that u is not a function of x, u is only a function of y, so then this term will also be 0. So we'll be left with rho u del u by del x is equal to mu del square u by del y square. Oh, but u is not a function of x, so then this will also be 0. So what will be left with? We will be left with mu del square u by del y square equal to 0. So let's just write it. Mu del square u by del y square is equal to 0. Okay, so we can solve this differential equation, and since u is just a function of y and not a function of x and z, I can write this partial derivative as complete derivative. Okay, so let's now solve this equation. So first integrating this equation with respect to y gives me a constant c1. Okay, then integrating this equation with respect to y will give me u equal to c1y plus some c2. Okay, now to get these c1 and c2, I'll use the boundary conditions. So what are my boundary conditions? So these were my two plates. This was moving with velocity u, this height was h, this has velocity u equal to 0, so this is fixed. So you can see that, and since this is y, this is x. So if at y equal to 0, what is velocity? So the velocity of fluid should be 0 because of the no slip boundary condition. And at y equal to h, the velocity of the fluid should be u because of the no slip boundary condition. Okay, so let's just quickly write it. So at y equal to 0, u equal to 0, this thing implies, so if I put y equal to 0, I'll be left with u equal to c2, but u is equal to 0 there, so c2 will be 0 there. Next, at y is equal to h, u is equal to capital U. So I'll have c1 equal to u by y, but y is h, so I'll be left with c1 equal to u by h. This implies my velocity profile will become c1, which is u by h times y plus c2, which is 0. So this will be my velocity profile. So this velocity profile will be linear. So if I draw this will look something like this. So it will be 0 here, and will start to increase, and will look something like this. Okay, so this is my velocity profile. So this, the first part of the question, we have solved it. We have solved the velocity profile of the fluid. The next question is, find the direction of the shear stress on the top and the bottom plate. Okay, so let's just do it quickly. So the shear stress tensor was this. Okay, now in our case, V is 0, so this term will go. W is 0, so this term will go away. So let's just remove all the terms containing V and W first. So this will be 0, this will be 0, this will be 0, and this will be 0. Okay, and next what we have is U only a function of y, so the partial derivative of u with respect to x will also be 0. The partial derivative of u with respect to z will also be 0, so this will also be 0. And now what we are left with is the terms tau yx and tau xy, and rest are 0. Okay, so we'll be left with tau xy and tau yx. So again, let me just draw the plates. So these were my two plates. Okay, this was moving at a constant velocity u, and this was held stationary, and the coordinate axes were, this was y, this was x, and this was z. So z is out of the plane. Okay, now the top plate has normal vector along minus j hat. So only shear stress tau xy, tau yy, and tau zy will be there on the plate. And since from just our previous argument, tau yy and tau zy are 0, will be only left with tau xy. Okay, and since this is acting along minus j hat, tau xy will be directed in this direction. Okay, alright, and similarly for the bottom plate, since the normal vector is along plus j hat direction, only again tau xy, tau yy, and tau zy terms will contribute, and tau yy and tau z are since 0, only tau xy will contribute, and this, since this normal vector is along positive j hat, tau xy will be directed in this direction. Okay, so this is the solution for our second part of the problem. Now let's do another problem. Oh, let me tell you that when, okay, so first let me just write this u, this is equal to, oh, I've written it over here. So such type of flows where the velocity is proportional to the distance in fluid dynamics, such type of flows in which you have a fluid between two parallel plates and one of them is moving with a velocity u, such type of flows are called cuvette flows. Okay, so the problem that we just did was the problem of a cuvette flow. Okay, now let's consider another example. So this is our next problem. It states that a fluid is flowing between two parallel plates. Again, the dimensions of the plates are same, length equal to L, width equal to W, a distance 2b apart. Okay, and that 2b is very less than L and W. Both the plates are held stationary, so this time there is no velocity of the upper plate and the bottom plate also, both are held stationary. And this time the one which is driving the flow is the pressure difference. So the pressure P1 is applied on this side and pressure P2 is applied on this side. So basically the pressure difference P1 minus P2, let me just write it with some other color. So P1 minus P2 is driving the flow this time. Okay, and now the question is to find the velocity profile of the fluid again. Okay, so since the geometry is same and the problem is nearly the same except the driving force, which is pressure gradient this time, I can again start with the same assumptions. So the first assumption is that now since this driving force is independent of time, this is some constant thing, so then I can assume that the flow should be steady. Okay, so I can assume a steady state flow. Next, again I can assume that the variations, because of the geometry, variations along x and z directions are negligible. This is not because of geometry, but it is because the pressure that you have applied is along the x-axis. So I have not shown you the coordinates, so let me just show you first the side view. So the side view will look like this. So this is my pressure P1, this is my pressure P2, these are my two plates. Okay, this is my plate 1, this is my plate 2, the length is L, this is 2b. Okay, and W is the width which is into the plane. Okay, all right, now let's consider my coordinate axis like this. So the origin is at the center of this, between the plates. Okay, center at the center of the distance separating the plates. Why I am taking this coordinate axis, it will be clear in a minute. Okay, so let's assume this to be x, this to be y, and out and the axis out of the plane as z. Okay, all right, now again from the geometry I can assume that the flow, so my velocity vector is only a function of y. Okay, and since I have taken variations along x and z directions negligible, I can say v vector is equal to u I hat, and since v is a function of y, now I can write v vector is equal to u, which is a function of y I hat. Okay, now with these assumptions in mind, let's write the continuity equation first. So we have divergence over v equal to 0, which will give us del u over del x plus del u over del y plus del v over del y plus del w over del z equal to 0, and since v and w are 0, I'll get del u by del x equal to 0. But since we have already considered u to be a function of y, I already know this beforehand. Okay, so continuity equation does not give me anything. Okay, so now let's consider the x, y and z momentums now, or the equation for x, y and z momentums. So this is the equation that we derived, okay, for x, y and z momentums. All right, now since again v and w are 0, let's first start with the equations that contain v and w terms. So since v and w are in y and z momentum, let's again start first with the y momentum. So solving y momentum equation, so we have considered steady state flows, so this is 0, and v is also 0, so anyway this will be 0. Again this will be 0, since there is another v here, this will be 0, v here, and this will be 0. Then gy is g, del p by del y is not 0 currently. Then we have v here, and v here. Okay, so what we are left with is rho g equal to del p by del y. So this implies that p is equal to rho gy plus some function which is a function of x and z. Okay, since this is a partial derivative, if I take the partial derivative, del over del y of this term, I'll get rho g plus, since this is only a function of x and z, this will give me 0, and that's how I'll get this. Okay, so that's why you should not forget about this f of xz. Okay, so this is what we get from solving y momentum equation. Now let's solve z momentum equation. So now let's solve this z momentum equation. Again, since w is 0, this will be 0, this will be 0, this will be 0, and this will be 0, and this and this will also be 0. Okay, and since in our problem the vertical axis is y and not z, rho gz will also be 0. So solving z momentum equation gives us del p by del z equal to 0. So this implies that p is a function of x and y. So since del p by del z is 0, p is only a function of y and x. Okay, now let's solve the x momentum equation. So again, steady flow, this will be 0. Since v is 0, this is 0. Since w is 0, this is 0. Since gx is 0, this is 0. Since u is not a function of x and u is not a function of z, this will be 0 and this will be 0. So what I'll be left with is del p by del x equal to mu del square u by del y square. So let's just write it. Solving x momentum equation gives us minus del p by del x plus mu del square u by del y square equal to 0. Okay, so what can I infer from this equation? Think about it. So I have said that u is only a function of y. Okay, so in that case, del square u by del y square will be a function of y or some constant, correct or not? Okay, Okay, all right. And since P is, if you see here, P is rho gy plus some function of x, then what will be del P by del x? Del P by del x is 0 plus f prime x. Okay, so what will this be? This will be either a function of x or some other function of x, g of x, or a constant. Okay, now let's say if it had been a function of y and if it had been a function of x, can I always get this plus this equal to 0? I want, right? Okay, now let's say if this was a constant and this was a function of y. Okay, I think I've written it wrong. So let's say this was a function of y and this was a function of, this was a constant quantity, then can this always be 0 at all y's? Of course not. So then what will be these two quantities? There will be nothing but constant. Okay, all right. So then we can write minus del P by del x is some constant c. This thing implies, and I can take negative sign here, and that negative of c will again be another constant c. Okay, so I can write del P by del x equal to c. Then I can write, integrating both sides, I can write this as p equal to cx plus, so let's call it c1x plus c2. Okay, now how can I get c1 and c2? Using boundary conditions. So using boundary conditions, what was my boundary condition? So these were my plates, these are my plates. At one end I had pressure P1, at other end I had pressure P2. This was my coordinate axis, x and y. So this was x equal to 0 and this was x equal to L because this length was L. Okay, so using boundary condition, at x equal to 0 my pressure is P1. This thing implies small C1 C2 is P1. Okay, and at x equal to L, P is equal to P2. So this implies P is equal to C1 L plus P1. Oh, sorry. So we want to find C2. Okay, C2 we already know. This pressure is P2, C2 is P1. So this thing by C1 will be P1 P2 minus P1 by L, but P1 is greater than P2, so I should write this as minus of P1 minus P2 by L. Okay, alright. So now since I want the fluid flow, the profile of the fluid flow, I'll use this equation. Since I know minus del P by del x now, so what is minus del P by del x? Minus del P by del x is minus C1. Okay, so then minus C1 plus mu del square u by del y square equal to 0. I can take C1 on the other side, this will become C1. What is C1? C1 is minus, I'm writing this, minus P1 minus P2 by L. Okay, now let's integrate this twice to get u as a function of y. So let's do it quickly. So let's take mu this side, this will become mu L. If I integrate it once, I'll get del u by del y equal to minus 1 by mu L. Let's call P1 minus P2 equal to delta P, so that we don't have to write it again and again. So this will be delta P. So integrating it once will give me a y plus, now since this u is a function of y only, I can write del square u by del y square as a complete derivative, del square u as del square u by dy square. So we don't have to now worry about the constant, so we don't have to worry about the constant as a function of other variables like x and z, because this is a complete derivative. I can just write a c here. Okay, all right, now integrate it again. I will get u equal to minus del p by mu l times y square plus cy. Let's say this is c1, or I've used c1 c2 already, so let's say this is c3. This will be c3 plus c4. Okay, now recall the geometry of the problem. So these were my plates, these are my coordinate axes, x and y. Okay, at this point the velocity is 0. At this point the velocity is 0 because of no slip boundary condition. Okay, all right, and if the fluid flow is a laminar flow, then can I argue that because of the symmetry of this problem, the flow should be maximum at the center and minimum at the surfaces, at the solid walls? I can do that, right? Because it's a laminar flow that we are studying, and from the symmetry I can say that at this point the velocity should be maximum. Okay, and since this point is y equal to 0 and this point is y equal to b, let's use the boundary condition now. So at y equal to b, velocity is 0, so just put y equal to b, or let's first put y equal to 0. So at y equal to 0, velocity is maximum. So if it is maximum, I'll have del u by del y, and since u is only a function of y, I can write it a complete derivative, del u by del y equal to 0, because this is a condition of a maxima or minima, right? So let's take the derivative of this side, derivative of this right term. What will this give me? This will give me minus over del p mu l 2y plus c3, and I am putting y equal to 0, so this will become 0. Let me just write it first. So at y equal to 0, so this will become, so this term will go to 0, so I'll get c3 equal to 0. Okay, so this was at y equal to 0. Then I have at y is equal to b. So at y equal to b, u equal to 0. This thing implies minus del p by mu l b square plus c3, which is 0, plus c4 equal to 0. So I'll get c4 equal to del p b square upon mu l. Oh, I forgot to putting 2 here. So while integrating y, I wrote y square, but I forgot to put 2 here also. Okay, so I'll get a 2 here. Okay, so c4 is delta p b square upon 2 mu l. All right, so what is my velocity? U. So u was minus del p y square upon 2 mu l plus c3, which is 0, plus c4, which is b square upon 2 mu l, which I can write as, by taking delta p upon 2 mu l outside, I can write this as b square by b square minus y square. Okay, so now let's just draw the velocity profile. So these are my 2 plates. Okay, in the middle of the separation between the 2 plates, I'll have velocity maximum and velocity 0 at the solid walls. So this this would look like this. Okay, this will be a parabolic profile. Okay, so this is the solution to our problem. Now let's take another problem where this time we have a cylindrical pipe. So the next problem states that consider an incompressible laminar flow in straight circular pipe with radius capital R. Consider the flow to be fully developed and find the velocity of the fluid inside the pipe. Okay, so I think this term is new. So let's first discuss what a fully developed flow means. So fully developed flow means that we can neglect the edge effects. That is, the region that we are studying, is far away from the entrance and exit of fluid. Okay, so it could be the case, let's say you have a pipe like this and you have a flow like this. Okay, because now it could be the case that around the entrance the fluid profile is still developing. Okay, but at the center the fluid profile that we want to find has developed fully. Okay, so this is what a fully developed flow means. So now let's focus on the problem that we are given. So we want to find a velocity profile of the fluid inside this pipe, and this is a pressure driven flow, and the walls of the pipe are stationary. Okay, now since there is a cylindrical symmetry in this problem, we should better consider the cylindrical coordinates and not the Cartesian coordinates, right? The cylindrical coordinates are theta and z. So in this case, let's say R is like this, Z is like this, and theta is like this. Okay, so I hope the concept of cylindrical coordinates is clear to you, that what is R, what is theta, and what is Z. Okay, so let's start with the assumptions. So the first assumption is, since the pressure P1 and P2 are not time dependent, my flow should be steady. Okay, second is, it's already given that it's a fully developed flow. This implies that along the flow in that direction, the dependence is not there. Okay, so if it is fully developed and we are focusing on only the part which is away from the exit and the entrance, then we have this scenario that the flow in that direction will not have the dependence in that direction. So in this case, since the flow is in z direction, so in this case del by dz will be 0. Okay, actually this is not a is not an assumption, but it is given to you in the question. It is given to you in the question that the flow is fully developed. So let's just write it somewhere down. Okay, so this was given to you in the question. But even if it was not given to you in the question, we could have still assumed it to be fully developed flow. Unless it is stated that it is not a fully developed, we can still assume it to be a fully developed flow. Okay, and the second assumption that we'll take is the axisymmetric flow. Now, since this wall or the cylindrical pipe is not rotating, okay, if it is not rotating, then the velocity v theta here should be 0. Well, VR and VZ will also be 0 here since it is not rotating, but let's just only assume v theta currently. So v theta here will be 0. Okay, and there is no driving force that forces your fluid to rotate like this. Okay, so then I can assume that v theta equal to 0, and there will be no variation along theta. Okay, so all the terms with del by theta will go to 0. Okay, so now with these assumptions in hand, let's solve the problem. So let's now consider, now since we are dealing with the cylindrical coordinates and not the Cartesian coordinates, first let me tell you what is divergence vector in the cylindrical coordinates and what are the x, y and z momentum equations in the cylindrical coordinates. Okay, so these are the equations in cylindrical coordinates. Okay, so we have velocity vectors, so our notation is v vector. So we have ur, or it will be v of r in our case, v of theta in our case, v of z. Okay, and it will be divergence over v vector, and you can write ur as vr, u theta as v theta, and along z it was uz as vz. Okay, so you can do it's simply replacing u with v if you want. Okay, otherwise you can stick with it that let's say this is u vector. Okay, so if u vector is given as ur as a function of r theta z and t in r hat direction, so this er is the unit vector along r plus u theta plus uz, then the divergence in the continuity equation will be given by this, and the r momentum, theta momentum, z momentum equations will be given like this. Okay, alright, so now let's first apply this continuity equation in our problem. So our continuity equation, okay, so let me write it, solving continuity equation. So let's see the continuity equation. We have 1 by r del by del r ur plus del u theta by del theta plus del uz by del z equal to 0. Okay, now I just argued that u theta will be 0. Okay, and since it is a fully developed flow, there is along the flow, since the flow was along z axis, along the flow there will be no variation in that direction, so del by del z of anything will be 0. So del by del z of not anything but the del by del z of the velocity will be 0, so that's why this is 0. So we'll be left with 1 by r del by del r ur equal to 0. So let's just quickly write it. So it will be 1 by r del by del r ur equal to 0. So if this is 0, I'll get RUR equal to 0. Okay, sorry, no, not 0 but a constant. Okay, now why this constant will not be a function of theta and z? Because since your u, which is ur r hat plus u theta theta hat plus uz z hat, since I just said that u is not a function of z, and since u is also not a function of theta, okay, this was 0, so that's why this u will only be a function of r. So I can write this u of r, ur, which is a function of r hat, plus uz, which will be a function of r z hat. Okay, so I'll be left with this, and that's why I can write del by del r as d by dr, since it will only be a function of r, and then this r of ur will be a constant. Okay, and will not be a function of other variables. All right, so now if you have this equation, r u r equal to constant, what can you infer from this equation? So you had a pipe, okay, and the fluid was flowing along this pipe, okay, and the coordinate axes were, this was r, okay. Now if I ask you what will happen at r equal to 0, what will be your answer? From this equation you will say at r equal to 0 ur will be infinite, but it is not realistically possible, so that's why this constant has to be 0. Okay, let me just write it. Since at r equal to 0 ur cannot be infinity, this thing implies, let's say if this constant is c1 is 0. Okay, so this is what we get from the continuity equation, that now if c1 is 0 and r is not 0, what will be 0? Ur will be 0. So from continuity equation we get ur equal to 0. Okay, and since u theta is already a 0, this thing implies my u will be, so this is a vector, u vector will only be uz, which will be a function of our z hat. Okay, so this is what I get from by solving continuity equation. Okay, now let's solve other momentum equations. Now what are 0? U theta and uz are 0. Ur and u theta are 0. So ur and, so from here ur and u theta are 0. So we'll first solve the momentum equations containing ur and u theta terms. So let's first solve the r momentum equation, which is this. Okay, now since it's a steady flow, this will be 0. Then again ur is 0, so this will be 0, this will be 0, and this will be 0, and u theta is 0, so this will also be 0. The flow is like this. So gravity is acting in this direction, which is r direction, so that's why I cannot take gr to be 0. Okay, then again ur is 0, so I can take this to be 0, this to be 0, u theta is 0, this will also be 0, and this will also be 0. To understand the problem better, let's also neglect the gravity in our problem. Okay, so then we'll be left with, for the r momentum equation, we'll be left with del p by del r equal to 0. So after solving r momentum equation, we get del p by del r equal to 0. This implies p is a function of z and theta. Okay, now let's solve the theta momentum equation. Okay, because u theta is also 0. So let's solve this. So u theta is 0, this 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 will also 0, this will also be 0, this will also be 0 since u theta is 0, ur is also 0, so this will also be 0. So what will be left with? We're left with del p by del theta equal to 0. So solving theta momentum equation, we get del p by del theta equal to 0. This thing as p is a function of r and z, but this tells me that so this tells me that p is a function of z and theta. This tells me that p is a function of r and z. So what I'll get p is just a function of z. Okay, so now let's solve the z momentum equation. Let's see what terms vanish in z momentum equation. So since it's a steady flow, this will be 0. Okay, then ur is 0, so this will be 0. U theta is 0, so this will be 0. uz is just a function of r, so then this will be 0. This will be non-zero because uz is a function of r, then uz is not a function of theta and uz is not a function of z, so these two will be also be 0. So then what will be left with is del p by del z equal to mu 1 by r del by del r, mu 1 by r del by del r, r del uz by del r, r del uz by del r. Okay, now again we can see here that p is only a function of z, then del p by del z will either be a function of z or a constant, and uz is only a function of r, then this thing will either be a function of r or a constant, and if these are equal, that only means that these two are constants. Okay, so now let's put del p by del z equal to a constant, and since p is only dependent upon z this time, so del p by del z becomes dp by dz. So del p by del z, which is nothing but will be dp by dz, because p is only a function of z. There will be some constant c1, integrating over z will give us c1z plus c2. Okay, now the boundary conditions were, so this was, let's say z equal to 0, and this was, let's say z equal to the pipe length L. So at z equal to 0, pressure was P1. So this thing by C2 0, C2 is P1, and at z equal to L, pressure is P2. So P2 is equal to C1 L plus C2, which is P1. So L will be P2 minus P1 by L. C1 will be P2 minus P1 by L. Okay, so, and since this del P by del Z is equal to mu 1 by r or mu by r del by del r, r uz by del r equal to C1, and C1 is, we just found, equal to P2 minus P1 by L. Let's say this is del P by L. So now I can solve uz as a function of r. Okay, so let's quickly solve it. So this del by del r is acting on this. So let's take r this side and mu this side. So what I'll get is, I'll get del p r. Okay, let me just write it another line. So I'll get del by del r, r del uz by del r equal to delta p by L r by mu. Integrating both sides back to r will give me del uz by del r equal to delta p by L mu r square by 2 plus, and since uz is a function of r only, this is actually d by dr. Okay. So that's why there will be a constant and will not be a function of theta and z. So let's say this is a constant C3. Now let's take this r on the right side. So I'll get 1 by r, 1 by r. Now again r equal to 0 will blow this term. So r equal to 0 will blow this term. Okay, and since this r gets cancelled with this r, this term will not blow. So the only term that will blow at r equal to 0 will be this. Okay, and at r equal to 0, obviously del u d by dr of uz cannot be infinity. So then what will be C3? C3 will be 0. Okay, since at r equal to 0, duz by dr is not infinity. Okay, alright. So then again integrate this. So you'll get uz equal to delta p by 2 mu r square by 2 plus some constant C4. Now at r equal to capital R, I know uz will be 0. So this same implies 0 equal to delta p by 4 mu r square plus C4, and I can take this term this side and will get C4 equal to minus delta p r square by 4 mu. So this implies that uz is equal to delta p by 4 mu r square minus r square, and there should be L also. Oh sorry, I forgot this L, so there should be an L for mu L. Okay, so this is our solution for the velocity. Okay, let's draw the velocity profile. So this was my cylindrical pipe. Okay, and again it will be maximum at the center. The velocity is maximum at the center is directed only along z. So the flow looks like, velocity profile would look like this. Okay, so such type of flows are called Hagen-Poiseuille flow, and the flow that we discussed in the previous problem, this type of flow is called plane Poiseuille flow. Okay, so I hope now how to use Navier-Stokes equation, the continuity equation to given problem is clear to you all. Okay, thank you for attending the lecture.